Here we are using the integral to compute volumes of rotated functions. So to review, you can use the integral to compute the area underneath a curve of any function, f of x, by taking the integral of that function over the boundary points. So say this is pi and this is 0. You would take the definite integral of that function from those 2 points to find the area under the curve. The integral can also be used to calculate the volume of any function, f of x, that is rotated around a given axis. So in this case, if it was to be rotated around the x-axis, it would create a shape with cross-sections that are kind of disc-like. And these discs would have a radius of the function, so f of x, and the area of a circle, their area would be pi times their radius, which is the function, squared. So to calculate the volume, you would take the integral from pi to 0 of that equation for the area. And this would give you the volume of that shape. But say you wanted to take this equation from 0 to pi and rotate it around the y-axis. This would not be possible because using disk cross-sections, because there's this empty space that gets formed in the middle. This is where shells come in.
Shells are washers whose inside radius and outside radius are determined by the same function, where the general integral used to find the volume cannot work. Rather than stacking disks, one can nest cylinders to find the volume of the rotated function.
So, to use cylinders to find this volume, they would have a height that is equal to the function, and a radius that is equal to the x value of that function. So we're only interested in using the outside wall of this cylinder, which is given by a surface area that is equal to 2 pi r times h. So in this case, that would be equal to 2 pi times x times the function. And you would take the integral of that from pi to 0. And that would give you the volume of that shape rotated around the y-axis.
Let's do an example. Say we have the functions y equals sine x squared and y equals 0, with boundaries from 0 to pi over 2, rotated around the y-axis. First, sketch the region of the graph being rotated around the y-axis. Then draw out the cross-section. In this case, the cross-section will be a cylinder, where the radius will be x and the height is sine x squared. For this problem, instead of the volume formula for the solid, we will use the surface area equation, which is 2 pi r h. When you plug in the radius, which is x, and the height, which is sine x squared, your surface area equation turns into 2 pi x times sine x squared.
This integral can be solved using u substitution. The first step is to spot the lurking derivative. So here, the derivative of x squared is 2x. We can set u equal to x squared, and the derivative of u is then 2x. This makes dx equal to du over 2x. And when this gets substituted back into the integral, it leaves you with pi times the integral from pi over 2 to 0 of 2x, the sine of u, du over 2x. The 2's and the x's both conveniently cancel. This leaves us with the expression pi times the integral from pi over 2 to 0 of the sine of u du. The antiderivative of the sine of u is the negative cosine of u, leaving us with pi times the negative cosine of u from pi over 2 to 0. Next, we have to substitute substitute x squared in for u, giving us pi times the negative cosine of x squared from pi over 2 to 0. And when this is written out, you get pi, and we can take out the negative, times the cosine of pi squared over x squared minus the cosine of 0 squared. And when you calculate this out, you get 5.6 as the volume of sine of x squared rotated around the y-axis.
Now let's put this into real-world context by finding the volume of the orbit around the Sun. The Earth, as it rotates around the Sun, follows a circular path, and with the Earth's shape, it creates a ring. The radius of the Earth's orbit around the Sun is 1.496 times 10 to the 11th meters. The Earth is a sphere with a radius of 6.371 times 10 to the 6th meters. The graph of x minus 1.496 times 10 to the 11th squared plus y squared equals 4.059 times 10 to the 13th, rewritten as y equals the square root of 4.059 times 10 to the 13th minus x minus 1.496 times 10 to the 11th squared, can be used to represent the top half of the Earth with the Sun at 0, 0. The volume of this semicircle as it rotates around the Sun can be represented by nested cylinders. These cylinders will have a height of the square root of 4.059 times 10 to the 13th minus x minus 1.496 times 10 to the 11th squared, and a radius of x, the distance from the Sun to their outer edge. The surface area is represented by 2 pi rh, and in this case, when you plug in the height and the radius of the cylinders, will equal 2 pi x times the square root of 4.059 times 10 to the 13th minus x minus 1.496 times 10 to the 11th squared. To find the volume, this surface area must be integrated from Earth's closest point to the Sun to its furthest point, from x equals 1.495 times 10 to the 11th to x equals 1.496 times 10 to the 11th. The integral will look a lot like this when done out fully, and when the math is done, the approximation of the volume of the Earth's orbit around the Sun is 2.237 times 10 to the 30th.